Okay, so here we are. Today Keith Henson will be talking. He founded the L5 Society, and we'll be talking about how to use power satellites to get off of our dependency on fossil fuels. Let me know when I can move to the next slide.
Oh, okay. All right. Well, L5 Society is probably something that almost nobody knows about. It's long ago. But anyway, it was involved with space stuff, and so I've been involved with power satellites particularly for a very, very long time. Much of this information is brand new. It really only developed after about April of this year. This is about ways to get the power, the parts for power satellites up, ways to get the energy down, and what happens when you build an awful lot of power satellites and start using them to provide energy. Next slide. One of the things that's been a concern recently is the rising CO2 in the atmosphere, and it just incidentally happens that besides solving the energy problem, this will solve the CO2 problem. I'll get back to this somewhat later. Next. Power satellites. They're an idea that's been kicking around since 1968, long time. They have never made sense because nobody tried to solve the whole problem all at once and get the cost of lifting the parts to geosynchronous down to a reasonable number. Next slide. There's a number of different varieties. This is one that actually uses lasers to get the power down because you can make them in smaller lumps than you can using microwaves, which are the much safer way. Next. This is another version that uses lasers. Most of the serious ones use microwaves, but there are a few ideas that have done it with lasers. Next. Why not ground solar instead of going to space to get it? It's plain a matter of economics. The problem is with doing it on the ground, you've got the biggest problem is storage, but you also get about somewhere 2.5 to 4 times as much sunlight if you can go into space in geosynchronous orbit. The orbit's tilted, so most of the year you don't even get cut off around midnight. However, the big influence on it, which more than doubles the cost of solar power on the ground, is if you want baseload power, the big problem of that is you've got to provide storage, and the storage is expensive, and nobody has ever figured out a way to get the cost of doing it down to a reasonable number. Next. This is something I swiped from one of Ed's papers up on this. This is from Stratosolar, and this shows the effect of the cost of things going down. But you have to multiply this by a significant factor in order to get the cost down, and you've got to apply the factor then to the difference between the capital investment and the prices per cent of kilowatt hour of power. And the number is roughly 8,000. So if you have a $1,600 per kilowatt or 1.6 billion per gigawatt, and you divide that out, you get about 2 cents a kilowatt hour. Next. Simple analysis. The U.S. government uses a figure of 6.8% in 20 years, which is 1 over 8,000. And this goes into the details, and then below there is what it costs to build a power satellite. You need to spend about $200 per kilowatt for the Rectenna, of which about $50 a kilowatt is the cost of the inverter that takes the DC power to AC, and the rest of it is parts and transport at 5 kilograms per kilowatt, which is a reasonable kind of number for the mass of a power satellite. It takes $100 a kilogram or less to GEO to get the cost down to where you can afford to build them at that price. Next. So the target here is 2 cents a kilowatt hour, but in order to keep a friend of mine happy about the thing, I start actually at 5 cents a kilowatt hour for the first power that comes down, which is cheaper than new coal, but it drops over the following 10 years to 2 cents. Next slide. This $100 a kilogram to GEO just simply can't be done with chemical fuels. I don't believe it can be done even with the most extreme efforts of reusability that the SpaceX people are talking about. I think they can get it to $1,000 a kilogram, but that's 10 times too expensive. Part of the reason for that is that the rocket equations give you a factor that is huge, so that you only wind up with a very small amount of payload. The Skylon, which I'll discuss quite a bit in here, can get it down to maybe $500 a kilogram, but it cheats. It uses part of the flight up with a burning air instead of burning oxygen on board, so it manages to get an extremely high exhaust velocity. Next slide. Equivalent exhaust velocity, actually. This is the mass ratio versus multiples of V sub E, and what this means is that you don't want to have your exhaust velocity much below 1, ratio of 1. So you want a velocity that's essentially the same, which means somewhere around 8 to 9 kilometers per second, which is hard to do. The next slide shows the actual equation, if you flip to the next. And this gives you an idea, if the delta V over that you want is over the velocity of the exhaust velocity is approximately 1, you wind up with a reaction mass fraction of the rocket being approximately 63%. Thus, the payload is 37%. If you go to LOX hydrogen, which has an exhaust velocity which is about half of that you need to get to orbit on here, you get 80, actually I think it's 80, yeah, it should have been, there's a typo there, it should be 86% reaction mass and 13.5% vehicle. Well, when you consider that a reusable vehicle requires about 15% structure, you can see that a reusable single stage to orbit just doesn't work. It's short a couple of percent. So if anybody knows how to lift, you can lift negative mass to space, but positive mass, no. Next. So the basic idea here is to use one power satellite to build, you build one power satellite the hard way. You equip it with propulsion lasers, which allows you to get much higher than chemical exhaust velocities, and you bring up the material to build hundreds using the first one. And you build more propulsion lasers as well, and you can undercut and displace the fossil fuels. Next slide. Well, here's one of the two keys to the thing. This is a vehicle that called the Skylon. That's a British UK project. The Reaction Engines builds this thing, or is designing it rather. That hasn't been built yet. But it's a single stage to orbit that uses air, burns air along with hydrogen to get into orbit, and it uses it burns air as long as it can, uses air as a reaction mass as long as it can, which is to say about a quarter of the way to orbit. Next slide. This is an incredibly clever idea. They actually managed to suck more energy out of the hydrogen than you get from just burning it. If you notice the circular items in the middle, these are what are called the pre-coolers, and what they do is they cool the incoming air from as high as 1500 degrees C down to minus 140. They do it in about 4 inches of time in about 1/100th of a second. And the stuff that they're made out of, next slide. This shows the heat exchanger on the thing, which they've actually built. This is an actual real picture, and that's the trickiest part of the whole thing. Next slide. This shows one segment of the thing, which you can see it's a countercurrent type heat exchanger where they run the fluid that's getting hot through it around this way, and the air moves through it the other way. There's a whole bunch of these put together. These things are made out of tubing that's so fine that these things look like fabric. They're so tiny, but that's just the consequence of trying to get a huge amount of surface area. In fact, one of these heat exchanger units has like 26 kilometers of tubing in it, and they managed something that I didn't think they could actually do, but they managed to figure out a way to furnace braze these things such that they hold helium. And it was a major effort to do it, but they've managed to do it. Next. And they tested it last year, last November. They fired this thing up, and they were just sucking air through the thing, and they proved that the frost control mechanism that they have on it, which I don't know, it's a trade secret, seeing they decided they were not going to patent any of it. They managed to test it, and indeed it met the specs of what they were expecting out of it. So it's a viable thing with a few tens of billions of dollars more work to develop, both to finish the development of the engine. However, they do have $60 million or 60 million pounds, about $90 million from the that they got right at the end of June for continuing the engine development with reaction engines. So at least the UK government is taking it seriously. Next. Skyline is mostly a huge fuel tank. It actually gets 15 tons to, the current version is 15 tons to LEO. The red on there is the hydrogen in it, and the tiny little blue tanks are the oxygen in it. It has 150 tons of oxygen and like 60 tons of hydrogen. Hydrogen is the least dense liquid, even liquid hydrogen is one of the least dense substances you can find. It's between balsa wood and goose down. So it helps because when you're actually bringing it back, the thing is extremely light, and unlike the space shuttle, which came in and decelerated pretty hard in running into the lower atmosphere, this thing actually does most of its deceleration 10 kilometers above where the shuttle did, and it glows only a nice orange. It doesn't come up to this white hot that the shuttle did. Next slide. The other piece is lasers that you need, and lasers have reached an astonishing level of development recently. They've gone up and up and up. This is a 15 kilowatt laser module, and I asked the guys that built this thing, this is Northrop Grumman that builds these little puppies. This is a continuous wave, which means you can run it all the time. It's not pulsed, and it puts out 15 kilowatts at a roughly 50% efficiency. And I asked them if you could gang the thing into the gigawatt level, and they said, if you have a long checkbook, no problem. So it's just a matter of cost. It's pretty expensive, but such is life. Next slide. The development of lasers in space is actually very, very advanced. They had a 4-meter mirror back, they completed the testing on this 4-meter mirror back in 1989 as part of the Star Wars project, and it was it's a fairly amazing business, but almost all this stuff was done, and the URL in the bottom of this has a great deal of information on it. They actually built segments of the mirrors that were up to 10 meters or 10 or 11 meters in there, which is way bigger than you need for focusing the laser light from GEO down to LEO. Next slide. The idea is, of course, is that you're heating hydrogen. So what you amount to is a big tank of hydrogen, and this is another beamed energy propulsion proposal. But you heat the hydrogen that comes out of the tank through a heater, and it goes on out the back. This is using microwaves, but it works even better with lasers. In fact, what you have is big spots on the wings of the Skylon that are nothing but masses of fine tubing that you pump the hydrogen through to heat it up. You have to get it to 50 kilograms per second of hydrogen going through there, which defines how high, and you heat it to 2,700 K, which means it goes out of the end at about 7.5 kilometers per second. And that takes a lot of power. It takes about 2.3 gigawatts, and by the time you have account for that misses the vehicle and so forth, it amounts to about 3 gigawatts of power, which is a lot of power until you start thinking about the Saturn V, which was actually putting out very close to 70 gigawatts when it was under power. So this is much smaller than a Saturn V, but pretty efficient because, of course, it uses the fuel much more efficiently. Next slide. This is a somewhat confusing slide, but this is the geometry of geosynchronous and low Earth orbit to scale. The Earth is not to scale in there, but what what it means is that you launch the Skylon, you fly it, goes off the runway, it flies up, gaining speed and altitude, gets up to about 10 to 20 kilometers up, and at that point you beam the energy on it and start pumping the hydrogen through the wings, and then it accelerates the whole vehicle into orbit. It takes a long time to do this, between 15 and 20 minutes, and it accelerates to orbital speed on hot hydrogen. Some people have said, why not water instead of, and the problem of it is that to get the same exhaust velocity out of water, you'd have to heat the water to 18,000 degrees. So it just plain hydrogen is really your only choice in this matter, and it is the big consumable of this because you're using hundreds of tons per hour to run this operation. Next slide. When you get into orbit, you release a secondary payload on it. This was some work that Reaction Engines did for me, showing how you could release one at a somewhat lower altitude than low Earth orbit. But the same principle. You open the payload doors, kick the payload out, close them up, and re-enter. In this case, you can re-enter after the first or any number of orbits and come back to the same runway that you started. Next. All right, the second stage here, which is 30 tons of which 10 tons of it is hydrogen, is released. It then, on the second orbit around, it gets accelerated over a long period of time using about 270 megawatts of power, which is about a tenth as much. And it accelerates up to what's called geosynchronous transfer orbit. And at that is a orbit that kisses geosync and comes down to 300 kilometers. And so 5 hours, it takes 5 hours to do that, and the power satellite has moved, the power, the laser, propulsion laser satellite has moved over by about 5 hours in the orbit, and so it reaches across, heats the stuff again, and accelerates the remaining the vehicle plus the remaining fuel that's in it up to circularizing the orbit at geosynchronous. This is the kind of thing that actually somebody else came up with the ideas on how to do this. There are many variations on this, but this was the simplest. Next. In terms of thinking about big lasers, there are people that are putting me in the shade. This is from Dr. Philip Lubman, who's actually at the University of Santa Barbara. I had San Diego on my mind too much lately. And this was the D-Star 4, which he's talking about, and apparently is talking extensively to military people and so forth about planetary defense. And the idea of this is a laser so big. This is a 100 gigawatt laser, which is 30 some odd times bigger than I'm talking about. And the idea here is that you could use it for dealing with comets or asteroids by simply evaporating the things over a period of time. Occasionally I think I have some grandiose sorts of ideas in mind, and then somebody comes along and just puts me in the shade. Next slide. Okay, well, last fall, I ran all of this into a model, an economic model, looking at the cost of developing the Skylon and buying the lasers and all the lift costs to get everything done. And it turned out that it was right around $140 billion to do it. And the payoff time in the thing was like, 12 years out. It pays off pretty fast once you get it all in place, but it takes a long time to do it. Next slide. And that's where it stood April 2. And have you ever had one of those, why didn't I think of that moments? Well, a guy named Steve Nixon, to give him credit where credit is due, he's somebody I've never actually met. I just know him in a chat room that I was in. And so he said, why don't you power it from the ground with using microwaves? Well, next slide. There's an engineering principle called reciprocity that says if you've got a couple of antennas, the gain between the two antennas doesn't matter which one you use for the transmitter and the receiver. So, next slide. This is a picture of a power satellite, but the same thing works in reverse. Here you have, instead of a receiver down here, you have an enormous transmitter that's 10 kilometers across and phased array. So it puts out a laser-like beam of energy, and it goes up and focuses on 1 kilometer diameter receiving antenna in space at geosynchronous. This starts out with 12 gigawatts down here. You get 6 gigawatts out of the antenna, and then it's a 50% loss in the laser electricity to laser conversion. So you've got 3 gigawatts out of the laser. Next slide. And it's lighter, cheaper, smaller, all the good kind of things. Instead of a 25,000 ton power satellite, the Rectenna that we're talking about here weighs less than 1,000 tons. It's about 960 or 70 tons, something like that. It's an amazing cut in the thing. In the next slide. And even better, you don't have to build it in GEO, which is very expensive, and we've never done any work in GEO to speak of. I mean, all the communication satellites are up there, but nobody's ever spent any time in GEO to try to put things together or to fix power satellites or anything, or to fix communication satellites. So you can build it all in LEO. And then transport the whole thing out. Next slide. That's a rough mass budget for it. The heat sink is the dominant factor on the whole thing, and there may be ways to get that down, but it involves a huge area because the only way to get rid of heat in space is radiation, and it takes about a square kilometer for each 500 megawatts of waste heat that you're getting rid of. So that's the biggest thing. The other piece of it is next biggest is the reaction mass that you need to get it up there. It takes about 20% of the total weight of the thing for reaction mass. And that's using electric thrusters to get it up there. And of course, you've got all the power in the world because you've got the Rectenna that's capable of running the laser. So you've got 6 gigawatts of power available. And in fact, if you use the performance figures that you can find for Hall effect thrusters and such things, you can get it works out that the whole thing gets from LEO to GEO in 10 days. It only takes 21 hours of actual thrusting to do it. So it looks like at first pass anyway, it looks like a deal on it. And you might note that while this is an awful lot of stuff to haul up into low Earth orbit, it's only about 20 times the mass of the International Space Station. Next slide. So, reworking the economics on the thing turns out to be very interesting because it cuts the time for getting the first power back to a little over 6 years. It cuts the peak investment to about $60 billion. And at the end of 10 years, you've got $300 billion worth of profit out of the thing. So the ROI for this particular little beast is about 500% roughly, which is exceptional. The yearly effective return on investment is around 52%, and the net present value of this thing, if anybody wants to buy it, is it's $160 billion. That's just I don't know how much of this is just total fantasy, but it's what you get when you run the functions on Excel. Next slide. And this just says what I said on there. And this is based on declining cost of power down to 2 cents. Peak investment, $60 billion. And one of the things about this is many of the people that have done this kind of work with power satellites have always assumed that you would sell power. Well, we already have power companies that do that, so why not just sell them the power plants? And it cuts the amount of capital that you have to invest in the thing by a huge amount if you just build the things and sell them. So doing that, you sell 100 gigawatts per year starting, and then the next slide. Oh, I don't know why this one wound up. This is the article. This is out of place for some reason. This is where the Indians and the Chinese were talking about committing to building power satellites last November. Next slide. And this goes through how you justify the numbers on it. Next slide. All right, this is where the rubber hits the road. If you reinvest a roughly 10% of the mass that flow that you're hauling into orbit into more lasers, you roughly double the capacity of building power satellites per year. This is on a quarterly basis, and you need in order to get up to the market that you really need, this project starts, the first propulsion laser is capable of lifting 500,000 tons per year to GEO, which is enough to build 100 gigawatts of power satellite. But you can grow it very fast, and if you grow it as fast as you can on this, within within about 17 years of startup, you're at hauling up a 250,000 tons, or sorry, 2,500,000 tons, so you're up to 5 times that much per quarter. So it's like 20 times as high. So you started out building 100 gigawatts per year, and now you're at building 2 terawatts per year. The total human demand for energy is up around 15 terawatts. Next slide. And this shows the installed power, assuming you stopped at building 2 terawatts per year. It shows the installed power that you get out there, and somewhere around 20 years into the project, or 22 years into the project, you've built enough power to replace all the energy that humans use. This is coal, oil, gas, nuclear. You wouldn't replace hydro, because hydro is still cheaper than this stuff is. So there's no point in doing that. Next slide. This is a rather grandiose business, but it's pretty clear that if you take the increase in carbon dioxide that we had from the first slide, and you figure that it's all coming from human activities, the rise in the CO2. If we quit burning fossil fuels, which we would if it was all replaced by cheaper solar energy from space, then you'd expect this to level off. And so the next slide shows exactly that. This is an incredibly simple model. The only thing I did here was assume that the displacement of it lowers the increase of CO2 to zero when you have 15 terawatts of solar power from space online. And after that, the declining part of the thing is on the assumption, probably wrong, that you use the additional power that you get beyond 15 terawatts to suck CO2 out of the air and put it back in the oil fields or something like that. It's not a requirement on there, but it would otherwise just level off at that. But you do notice that it does level if you start soon and you do this incredibly fast but very, very, very profitable expansion on the production capacity of power satellites. It does indeed stop you short of the magic 250 ppm that they're talking about as being the disaster point. Next slide. And I think, now we come to something where I can actually use some help. It is lasers, big lasers, gigawatt scale lasers in space are, like it or not, weapons. And I don't know, it may be possible to figure out some way to put them under sufficient level of control that nobody will use them for weapon purposes, but they are weapons. And it becomes an interesting problem about how to do that. So if anybody has any good ideas, since this is completely out of my field, of how one might possibly figure out how to put this, how to take out the military aspect of these things, I appreciate thinking about it. So, and that's it. Any? All right. I'm not sure that anybody, there's so much of this thing that I suspect it leaves people more boggled than anything else.
So I understand that you use, when you use big arrays in the ground to initially get the power up there.
Right.
How will you transfer power back to the ground?
Repeat the question, Keith. 'Cause I didn't
Yeah.
take the microphone.
Okay. The question is, how do you get the power back? Same way as it's always been proposed to get it back, namely microwave transmitter up there. In fact, the only thing that I'm doing to get the initial power for a short length of time to run the laser, because as soon as you've got enough stuff up there, you replace the rectenna that you've got in space with a power satellite, and the next power satellite that you build, you reverse the whole thing and start sending energy to the ground again. Via microwaves, yeah.
The only problem with the laser is to start.
Huh?
The only problem with having a gigawatt laser is to start.
The laser is necessary to get the cost of hauling all this, hauling 10 million, eventually 10 million tons a year of parts to space.
But your weaponization problem.
Oh yeah.
The first,
No, the weaponization. I mean,
or
the,
is persistent?
it's persistent problem. Because among other things, one of them isn't enough. You need to build 20 of these things eventually.
So I think that's where I've got the issue. How are you using lasers to lift things from the fire?
Ah.
Are you just shooting it Skylon from above
Yep.
instead of from underneath?
From above. You can't shoot it at it from underneath because it's ripping across the sky on the equator over the ocean, and you can't unless, and it was just, you might be able to put 10 or 12 of these laser systems on the ground on the equator, but the cost gets insanely high. So it just doesn't, and the utilization is very poor. Utilization of this thing is essentially that you launch one, you accelerate it from the top of its aerodynamic flight into orbit, and then you switch back and launch the next one. So and the beauty of this thing of it is that if you're under this particular circumstance of launching two geosynchronous from a fixed place on the ground, the launch window is always open. You can fly the thing, it's completely arbitrary. Any second, any minute kind of thing is a good time to take off. So you can run this, the problem is getting the thing up to high efficiency to where you can run it all the time. Because otherwise the laser is just crazy expensive. As it is, the laser costs about 40 or 50% of the allowable money that you can spend to get stuff up there. But if you run at halftime, it's twice that. So it gets to be insanely expensive if you do it. People have talked about, and the NASA people have talked about building one of these things to use for launching payloads like once a year. And the cost per kilogram is just completely insane if you do that, if you give any cost consideration to the capital at all.
One solution to your political problem might be to have a kill switch that requires, for example, 8 or 12 activations of the laser. So, for example, if for some reason it's been seen to be used in a confrontational or a conflict situation, the members of the Security Council will be monitoring this on a second-by-second basis constantly. Can all agree to press the kill switch within 2 minutes?
That's a possibility, but don't forget that any kind of thing that can be done with the interlocks can be undone.
Yeah, but to some point, then you're talking about a case of extrapolating viral cycles. Either you take a situation, a scenario that you put in place, you have a set of solutions. You can always say, well, anything can be stopped. The only way not to have the risk is then not to put it up.
Right.
Take that approach.
Right, and the idea is there are several thoughts on it. One of them is to limit the thing to where it simply cannot, the mechanism on the thing, which could be changed too, but it would take a big job to do it, where the mechanism of it would only allow the thing to sweep along the equator, which would help. And the business of multiple controls and multiple people being able to turn it off, people have even suggested that you leave the initial system of powering it from the ground on so that you could always shut it down from the ground. But, you know, if China's got the ground station and the laser, propulsion laser in space, that's sort of pointless.
So sorry, I'll
You go continue.
but basically, just then saying, one solution might be just to have the sweep over the ocean,
Yeah, well,
over the ocean, and that be the flight path?
right. Along the equator. There's a,
Over the Pacific, say.
well, there's only a half a dozen or a dozen places that you want to do this. One is right at the mouth of the Amazon, for example, if you're going to launch across the Atlantic. There's more places in the Pacific. One of the best places is the Maldives. But we've got to do that. We'd have to do that really quick because if the ocean comes up, they're gone. I think the high point is 6 feet. So, and then for every launch location, a couple of thousand kilometers to the east is, but along a much more of a potential place on the latitude on it. You can put the power plant on it. One of the possibilities, if the U.S. did it, would be to put the microwave system around in Los Angeles and launch from a place called Christmas Island, which is out south of Hawaii. Somebody else had you had one?
I did have one question, yes. When you showed the graph of numbers going up and to the right and positive money, it seems like a no-brainer. Have you tried getting investments for this? What are the challenges you see?
Well, if you want to write the $60 billion check for me, I'll probably take it. I haven't even thought of that. This is more of a. I'm not qualified to run something like this. I'm not even looking for funding on the thing because I'm not qualified to do it. It's so big. I mean, even $60 billion and all that profit that you can make out of the thing is probably beyond anybody in the Western world. I think it's far more likely that the Chinese will do it. They've already expressed an interest in power satellites themselves, and if anybody does it, they're more likely to do it. Incidentally, one of the problems that you have that can kill the profit on the thing is if something like fusion, really cheap fusion comes along, or any other cheap, nanotechnology, photovoltaic paint, or some other kind of trick like that. All of those kind of things would kill the cost of electric power below 2 cents a kilowatt hour. Well, not if you've already. Did you ever hear of something called Iridium? It was a huge project back in the 90s to build a 70 some odd satellites to use for cell phones, the equivalent of cell phones. It's still in existence today. If you want to talk from the South Pole, it's one of the few ways that you can do it. But they went bust because cell phones ate the market. Their model of the thing didn't include the changing, the extreme change that went on in the cell phone market, and the cell phone companies took their market.
But there is a difference here. You're talking about a solution for market saturation. So when the demand for power is way beyond the capacity to produce that power.
That's true.
So if all terrestrial solutions of cell phone towers, it's just crazy over capacity, with an Internet of Things by 2030, we have 100 times the data transmission requirements, for example, then these solutions may start expanding into play.
Yeah. But anyway, well, that's not the only thing it could do it. I mean, a plague that wiped out a substantial fraction of the human race would probably also drop the demand for electricity and the cost for it. Yes. There's any number of things that could happen. Yes, Monica.
So technical thing, I looked at the high cost of the
Yeah.
Up there. Could you get by with much more heat sink if you lower the duty cycle?
Yeah, but you don't, and that's actually not a bad idea because the initially you're limited by the number of available Skylines. You don't have enough, although you could push the production of them up. I haven't optimized this thing at all. But yeah, that's a possibility. Because you could indeed, there's a lot of thermal storage in something that's, 6 square kilometers.
So this is all also under the assumption that Skyline is completed and running?
Well, that's part of what the $60 billion is for.
Okay, so that includes funding the completion of Skyline?
Yes, 20 some odd, more than $20 billion of it is funding Skyline. Oddly enough, Skyline doesn't actually have any use except building power satellites. It's too much capacity. You can fly the thing every other day. There isn't 15 tons every other day going into space and won't be ever for communication satellites. In fact, it's tending to go down. The thing is just total overkill, even if you build just one of them. And building one is, crazy because the cost really doesn't come down until you're flying the things. You're flying 100 of them or 150 of them every other day. Huh?
How many flights?
72 flights a day. I mean, it's pretty easy to work it out. You're dealing with a need for 500,000 tons per year. And if you divide that by the 80,000 hours roughly per year, or 8,000 hours per year, it comes out to be 60 tons per hour, which is 3 20-ton vehicles every hour. By the way, one of the more interesting things that I actually did think of on this was, although it's not new, having been in science fiction for decades, is that you scrap the Skylines, not Skylines, you scrap the second stages. You're building them in huge volumes, 72 of them a day. So they're produced like trucks practically. You're dealing with a production line for the things, and there's so many of them that you can get the cost of building them down to almost nothing, and you preload the whatever cargo you want in the things, and at the last moment you fill them up with hydrogen in the Skyline as part of the fueling process. So they're pretty cheap. They're worth $100 a kilogram at GEO. So you just scrap them and run them and use the materials for the construction of the power satellites. It turns out that in space, particularly, industrial level machinery is very productive. Do any of you know who Eric Drexler is, by any chance? Some of you do, but he's the guy who sort of popularized the term nanotechnology with his '86 book. But Drexler and I were working on the space business back in the 70s, and we designed up a vapor deposition system for building very, very large structures. And it turns out that the thing would vaporize its own weight in aluminum or steel every 8 hours. So it doesn't take a whole lot of industrial machinery up there to convert whatever the things are built out of into useful things like sheet metal or I-beams or whatever.
I don't know much about this stuff, but maybe it's a naive question. But so, what are the issues with microwave and gigawatts up and down? You don't fry birds, you don't.
No.
Things like that.
In fact, they actually ran a long duration study of birds in a cage. Avco Everett did it way back in the 70s. And they realized that there was going to be a problem with birds and microwaves at that level. The microwaves are not at a very high level. They're in the 200 or 300 watts per square meter level. But they're, of course, are converted to electricity much more efficiently than solar cells, so you don't really need a very big area of them, relatively speaking.
So if you can do this.
Oh, the birds.
We're not birds with any, I just use birds.
Yeah.
So then why don't we use microwaves to, why do we have all these transmission lines? And we have all
Loss. It's the loss. The loss is about half. So it means that if you're going to sell power on the ground, you have to make it in space for a penny a kilowatt hour because you lose half of it. On the other hand, you're transmitting at 40,000 kilometers, and normally speaking, that would cost you 40 cents a kilowatt hour to transmit it on power lines on the ground.
But so then could we just lose it and transmit directly to homes?
No, it turns out that the optics won't let you do that. I mean, you can with lasers, but the idea of yeah, they need to, the optics. You know diffraction limits of optics. It's 200 years old, and you can look up Airy's disk and stuff like that. But what it amounts to is that the best you can do from a 1 kilometer transmitter in space is about 10 kilometers on the ground at 2.45 gigahertz, which is the normal frequency that's been studied a lot. There's possibilities of doing it differently, but that's the best one for getting through the atmosphere. Even a big thunderstorm doesn't necessarily kill you. Some more.
I just want to point out that it's called microwaves, but it's not the same microwaves as the microwave oven, because those
Actually-
are the frequencies of rapid water molecules around. If
Well-
different frequencies, then it doesn't happen.
Actually, it turns out it's very close. And in air, it doesn't seem to actually absorb much. But a microwave, by the way, under the antenna, the idea is to put the antennas over farmland so you don't have too much land expense for the things because they're transparent enough that the light gets through. But under the antennas, the intensity of the microwaves would be pretty much the same as you get from standing in front of your microwave oven heating up a cup of coffee. So it's not considered to be a problem.
Did I understand you right, that part of this process involves physically assembling things in the low Earth or stationary orbit?
Right.
Do you foresee any logistical problems if we have to essentially build a manufacturing plant in space?
I worked that out actually, and it turns out that I've thought about, for example, bringing up the beams for the structure on the thing as coils of wire, coils of sheet, and running them through a thing called a roll former. Have you ever seen guys putting gutters on a house? They have a machine that just takes a continuous roll of aluminum and folds it into a gutter and comes out. You get 50 feet long gutter, and you put it up with one with no seams in it. So.
I guess what I was imagining is is this roboticized? Do you need staff?
Living
Structures?
It's one of those, that particular thing of robots or non-robots is not it's not a serious consideration. We can do it either way.
One of the guys that's just joined our team is Jeff Hoffman, who was the lead astronaut for the Hubble mission. And we're in a different project, a space-based project. But he's just joined our team this year, and the characterization of what's needed to assemble large structures in space is now well within the technology requirements we have, the software control, which is key. So we can automate to a great extent now, but you still need people in situ to characterize the unstructured anomalies. So things that go wrong, that the robotics is still just outside of their capability. And maybe in 20 years' time, there's all sorts of things that can be done robotically end to end.
Human can do anything. It says, look, if someone can communicate what they need to do to them, they can
Right.
do literally anything, whereas
And a machine could do a million things correctly within a reasonably structured environment, even to some extent unstructured. But when it's that one thing that stops your supply chain,
Right.
stops your revenue, it doesn't matter that look, dude, it's just one thing.
It
And you still need people there.
it,
So
it turns.
Just to clarify, it sounds like you need 100 experts or debuggers as opposed to 50,000.
You probably need more like 50 iron workers.
it's a combination of very capable oil rig.
yeah.
Yeah.
And you can also have a lot of smart
But-
people on the ground talking to them, being like,
Tele-assisted.
yeah,
So we need whenever people get the space station deployed, as opposed to we need to build no grids.
It turns out that it doesn't matter. 500 people in space takes an amount of habitat that's much smaller than the jig that you need to build the power satellites, and it's like 500 people is like the total supply that they need to, if you were just not even growing any food there. it winds up to be like 1/3%. It just falls into the noise level on the design. Back to the thing about birds. The thing that they're going to have problems with birds is not them flying over and being incinerated or cooked or anything like that, but in a cold night, they found that the birds were all jammed up against the microwave horn. So what you can expect, the big problem that you're going to wind up with, I think, is, you know, one of these rectennas being covered with birds out there, you know, 10 million birds roosting on the dang antenna in the middle of the wintertime.
You've got no problems with Burning Man at Thanksgiving.
Sorry.
Yes, one question. I know that the locations in GEO are limited, so how these satellites affect?
It turns out that the reason that they have slots in GEO is because of this beam spread from the control and data transmitters on the ground. They're small, relatively small, you know, big as this room, but they generate a relatively wide beam out there. So you can't have two of them in the same slot. Power satellites doesn't matter. Yeah, you're transmitting back to the Earth, and the beams don't interfere with each other, so you don't have any problem with that. So you can put it, you know, you can put them, many of them up there. Back here.
Yeah, I just wanted to understand. You said you generate power at 1 cent per kilowatt hour in the space.
Sorry.
You said you generate power at 1 cent per kilowatt hour in the space.
1 or 2 cents per kilowatt hour from space. Oh, 1 cent per kilowatt hour in space. Yes.
So, is this, what technology is that?
Doesn't matter. Solar cells will probably get down that low, especially the lightweight ones. But you can do it with thermal as well. Thermal has some advantages. Are any of you familiar with the 774, 775 carbon-14 anomaly? Anybody know about that? It's worth looking it up because they found this ring in the where apparently the solar system and the Earth in particular was on the receiving end of a gamma ray burster, and it jumped the carbon-14. Apparently, it happened in like seconds, and it jumped the carbon-14 count in that year by about 20%. So it was a nasty event. We were looking right down the barrel of a gamma ray burster, apparently, that was fairly nearby, and I think they'll probably figure out which one it was sooner or later. But being in space is, I mean, I don't know what that would do. I haven't yet figured it out, but I think that might possibly kill solar cells, that gamma ray burst. And just, you know, we're dealing with something that happens in 1 second and they're all gone. Where you could pretty easily shield from that kind of a radiation, gamma ray radiation, the control electronics. And if you're using thermal, you know, steam turbines basically, and big radiators and such stuff, there's no reason that they would be hurt by something like that. Now, whether anybody is going to be concerned about an event that only happens 2 or 3 times per, you know, 10 millennia is anybody's guess, but it's something that I think should be considered, because if the world was highly dependent on power satellites, and true, we would have enormous stores of fuel, especially if we were making it and pumping it back into the oil fields. We could probably get by until we could recover from that, but nonetheless, it would be a very nasty thing all of a sudden to have 15 terawatts of power disappear.
Sorry, I just had one follow-up question.
Sure.
The economics of it, you worked it out. So the size that you've chosen right now for power satellites,
Right.
is there a reason
Yes.
that size is chosen?
Yes, they come in inconveniently large pieces, and it's due to the optics, microwave optics. That's the whole problem. The problem of it is that you can't really build one that's much smaller without it being much more expensive per kilowatt hour. I should point you to if you go looking for Seth Potter and power satellites, there's a PowerPoint presentation that he has, and I think page 30th slide or something like that into it has a detail on this on the economics.
Okay.
One more. Okay.
One more.
So have you considered have you integrated into your model the cost of these 10 square kilometer receivers on the ground? Because you talk about
Yeah,
generation.
they're about $1 billion a piece.
Yep, I'm not disagreeing. What I was trying to say was not just the cost of land, but the cost of transmission from there to end point.
Oh, from there? Well, the addition is about, the addition number is, the rough addition number on that is 1 cent per kilowatt hour per 1,000 kilometers. So if you can put these things within 400 or 500 kilometers of a city where the load is or wherever the load is, probably the average load would be under 200 kilometers away. So we're talking about, tenths of a 2 tenths or so of a cent additional for the transmission.
Okay.
Thank you.